Hello and welcome to our presentation Learning Feedforward Control for Laser Powder Bed Fusion. My name is Colin Reiff and I'm from the Institute for Control Engineering of Machine Tools and Manufacturing Units at the University of Stuttgart in Germany. In laser powder bed fusion, a powder layer is melted by the energy input of a laser and thus joined together. The laser is guided by a so-called galvanometer scanner. However, complex interactions within the build process and external disturbances can lead to unpredictable results. These can cause poor part properties and geometric inaccuracies, limiting the economic efficiency of the process. In industry and research, extensive efforts are made to understand the process interactions by modeling and simulating physical phenomena and process behavior. However, these simulations are extremely computationally intensive and therefore require a long waiting time until the results are available. Furthermore, these process models and simulations cannot describe the process in detail in its entirety, since it involves complex and highly dynamic interactions. Therefore, these approaches are limited to certain process states, system boundaries, and part geometries. In addition, unknown and stochastic influences, such as heterogeneous material properties, the inert gas flow, or the non-uniform heating system, have a significant impact on the process outcomes. To counteract these limitations, a high dynamic control of relevant process parameters, taking into account the transient process conditions, is indispensable. Currently, relevant process parameters are often kept constant since the use control systems do not offer real-time capable interfaces for intervention. In industry, special control boards are used to command the galvanometer scanner and laser source. These boards are processing set point lists in a typical cycle time of 10 microseconds required by the galvanometer scanner. The set point lists contain the geometric information about the path to be exposed and are transferred to the control board via a PCI Express interface before the process starts. Due to the PCI Express interface and the mentioned list format, the set points cannot easily be changed in real time during execution. Furthermore, the commercial control boards offer no possibilities to integrate customer-specific logic or to adjust the algorithms running on the controller. Consequently, no closed loop or advanced control strategies can be realized. However, the control boards can also not be easily replaced by conventional controls or real-time operating systems because they cannot fulfill the required cycle time of 10 microseconds. In order to obtain the necessary freedom and to be able to change parameters during the process, we have developed a new control architecture. Our architecture consists of an industrial control system, here Beckhoff TwinCAD 3, and a custom interface card connected to an FPGA board. The industrial control contains a CNC and PLC. This enables to use conventional NC programs and a wide range of CNC and PLC functionalities, such as the motion control, including the interpolated movement of axes. Furthermore, the industrial control provides multiple interfaces which enable to extend the overall system with real-time models, additional sensors and actuators. As I mentioned before, the industrial control only achieves a minimum cycle time of 50 microseconds, which is too slow for controlling the galvanometer scanner. Therefore, a high-frequency FPGA is necessary, which is connected to the higher level control via a real-time capable field bus. In this case, we use EtherCAD. The main task of the higher level control is running in a cycle time of 100 microseconds, generating the trajectory and commands for the scanner and laser source. Due to the slower cycle time, the generated set points have to be interpolated. By doing so, every 100 microseconds, a package containing the set points is generated and transferred to the FPGA. The FPGA design contains different functional components such as an EtherCAD slave controller and the XY2100 protocol used for communicating with the scanner system. Our custom control card provides a standardized interface for the galvanometer scanner and laser source. Here we can see the HMI of the industrial control system. We can load and execute NC programs containing the laser power, laser on-off signals and the positions for the galvanometer scanner. The use of the CNC also allows us, for example, to manipulate the scan speed during runtime. This is a short video demonstrating the functionality of the control architecture. Due to the standardized protocol for communicating with the galvanometer scanner, we can use a wide range of different scanner systems. The developed control architecture offers us now a wide range of different possibilities. We can, for example, adjust process parameters such as the laser power and scan speed during runtime, as done in our learning feedforward control. Furthermore, we can select the area to be exposed during the process. But also high-frequency, closed-loop controls running on the Fpga are thinkable. We also use the control to combine the galvanometer scanner with conventional access to increase the possible scan area. In the following, I would like to introduce the learning feedforward control approach. Frequent challenges in laser powder bed fusion are, for example, speed reductions caused by direction changes or contiguous scan vectors accumulating the applied energy in a relatively small area. This can lead to local overheating during the process if the laser power is kept constant. In order to counteract this problem, compensating movements, also known as skywriting, can be inserted with the laser switched off to ensure a constant processing speed. However, this measure increases the required build time and thus reduces the efficiency of the process. So we would like to adjust the laser power depending on the actual scan speed, taking also unknown influences into account. So how is the learning feedforward control working? In the beginning, we have an NC program containing the information for the laser source and the galvanometer scanner. The NC program is interpreted and executed by the CNC control. Using the scan speed calculated by the CNC, we can look up the according laser power in a three-dimensional map. Next to the scan speed, the laser power is also defined by the current powder bed temperature. This information can be won by a measurement or, like in this case, by a real-time temperature model. However, also other metrics instead of the powder bed temperature can be used. For example, the position of exposure on the powder bed or the number of already sintered underlying layers. To realize the learning process, a feedback signal is required, which allows to make statements about the achieved quality. In this case, a simulated null pool intensity measured with a pyrometer is used as an exemplary feedback signal. The calculated error of the desired and measured null pool intensity is used as input for a radial basis function network, which updates the map. The learning approach has the advantage that no initial relationship and consequently no time and cost-intensive parameter studies are necessary. By iteratively adjusting the functional relationship between laser power, scan speed and powder bed temperature during the process, the optimal map is learned over time. By the use of a second parameter, here the powder bed temperature, besides the scan speed, we expect to determine a more suitable laser power trajectory compared to approaches trying to achieve a constant energy density. Currently, we only have validated the control approach using our implemented thermal model and not using a real machine. However, our first results showed that compared to constant processing parameters, the standard deviation of the temperature along the scan path could be reduced by 83% for the here shown use case. In addition to this scenario shown here, we have tested and simulated further use cases. On average, the standard deviation of the temperature could be reduced by 48% for all simulated use cases. Next to the learning feedforward control, we have also implemented an approach to select the area of exposure during runtime, which I would like to introduce in the following. The goal of the online working algorithm is to determine a suitable order of exposure of single islands. Doing so, we hope to homogenize the powder bed temperature by actively influencing the timing of exposure of a certain area. Influencing this timing, hotspots have time to cool down, or colder areas can be preheated by the heating system of the machine. In contrast to current solutions, the order of areas to be scanned is determined during the actual build process. For this purpose, a three-dimensional model is cut into layers and an island scanning pattern is applied using a conventional slicer. Each island is subsequently stored in a separate NC program. A main NC program in turn references all the subprograms like shown here. The TwinCat3 control software used for the open control architecture offers the possibility of transferring so-called external variables to this NC main program during runtime. These variables contain the information about the next NC subprogram to be executed. The choice which NC subprogram should be executed is calculated in the PLC on the basis of the measured, or like in this case, of the calculated powder bed temperature. Using the online selection of the order of exposure, the standard deviation of the temperature could be reduced by 20% for the simulated use cases in comparison to the conventional scan strategies. As a result, hotter areas have additional time to cool down, which reduces the temperature gradients and thus the resulting residual stresses. We introduced a control architecture based on an industrial control system sending the determined set points to an FPGA via real-time field bus. The novel control architecture is used to implement a learning and model-based feedforward control. In addition, an online working algorithm for selecting a suitable order of exposure was implemented. The developed control strategies were validated using simulated use cases based on the implemented temperature model. In future work, an experimental validation of the developed control strategies will be performed. We also plan to improve the currently used thermal model by building an artificial neural network for predicting the powder bed temperature. Furthermore, we will use the new control architecture for the combination of galvanometer scanners with conventional linear axes. Thank you for your attention, and if you have further questions, please contact me. Thank you.